Hi, my name is Laura Barshik, and this is my presentation looking at data for people with cardiovascular disease. So for years, heart disease has been one of the leading causes of death in the United States and worldwide. I spend a lot of my time at home responding to EMS calls, and I unfortunately see patients with cardiovascular disease very frequently. Some of these people maybe are just having chest pain, but other times we get called for cardiac arrest. So cardiovascular health is, of course, very important, and it should be something that's talked about more because there are many factors that can cause cardiovascular disease, and some of these are definitely preventable. I hope to be a doctor in the emergency room in the future, and cardiovascular disease is something I will encounter very frequently, and I hope to be able to tell my patients what will really help for the future. If the disease progresses enough, it can lead to heart failure, which is what my data set is looking at. So the dataset has a list of information for each patient. There are some demographics, including age, gender, and general health information, including if they have high blood pressure, diabetes, if they have diabetes, are anemic, meaning they're red blood cell deficient, or if they smoke. All of the general health information are potential risk factors for heart failure. There are also different levels of molecules in the blood, and the normal range, these values should be around the slide, including the maximum and minimum that are in my data set. Creatine is an enzyme that is a waste product for muscles. High levels of creatine indicate stress or injury to the heart or other muscles. There are two slightly different measures of the levels of creatine in the blood in this data set, which are labeled creatine phosphokinase and serum creatine. There's also another blood component, serum sodium, to show how much sodium is in the blood. Sodium is super important in the body, so high sodium levels are a risk factor for people with heart conditions, but low sodium levels are much more dangerous and can lead to death. The last variable gotten from the blood is the platelet count. Low numbers mean the blood isn't able to clot properly, and high numbers mean the blood could clot spontaneously in the blood vessels. Ejection fraction is a percentage of how much blood is left in one of the chambers of the heart with each contraction. The last part of the data is whether the patient died by heart failure or not. Overall, this data set will allow me to take a look at some features that could contribute to mortality by heart failure, and knowing which features are most important will hopefully allow people to do what they can to minimize their risk. So after I had my data set, I imported it into R. The top table is what the data looked like in Excel before I imported it, and the bottom table is what part of the data looked like after I finished cleaning it. Overall, the data was pretty clean. I didn't have any problems with missing values or obviously incorrect values. All of the categorical variables that were the patient demographics were entered as 0 and 1, so I changed those to say no or yes. The platelet variable also had a really large range of numbers, so I changed that to a categorical variable with 5 options, ranging from severely low to high. I also made the age variable into a categorical variable with age ranges in 10-year increments. Some of the smaller cosmetic things were renaming the column names and taking out all of the old variables with 0s and 1s, except for the death variable, so I could use that for logistic regression later. So after I cleaned up the data set, I started manipulating some of the variables to see what information I'd be able to get from the data. Using the select function and excluding all the answers with no, I found that there were only 2 people that had all the risk factors, including diabetes, high blood pressure, anemia, and smoking. Out of the 400 people included in the dataset, 96 of them lived. There were only 83 patients that had low sodium, which is defined as being less than 135, and the average sodium level was 136, when the normal range is 135 to 147. High creatine is above 1.3 for men and above 1.1 for women. There were 54 men and 47 women that had high levels of creatine, which were calculated using the WICH and SUMMARY assumptions. The overall average ejection fraction percentage was 38%, which is much lower than the normal range of 50 to 75% and below 40%, which is considered a high risk for heart failure. The average ejection fraction of those who died was lower at 33%. And the age variable had a wide range from 40 to 90 with an average of 60. Most people in this data set had a normal level for their platelet count, with only 2 out of the 299 patients having a severely low platelet count. And these are some two-way tables with categorical variables. For the first table on the left, there are more males than females in this data set, but a higher percentage of females died. The middle table is looking at age when made into a categorical variable in ranges. These aren't in percentages, just counts, but you can tell that overall more people are smoking in the higher age groups. For the last table, I've been looking at risk factors and which one had the most deaths. Of all the risk factors, the highest number of patients that died while having the medical condition was anemia with 46 deaths. And so I took my data and started making graphs with it. These are two stacked bar graphs with both two categorical variables. These are percent stacked bar graphs and is presenting a slightly different way from other stacked bar graphs by telling the percentage of counts. The graph on the left is showing the variables death and gender. I thought it was interesting that almost the exact same number of men and women died in this data set. And the graph on the right is showing patients who smoke by their gender. Smoking had the greatest female versus male difference of all the categorical variables. You can see from the graph that there's a much higher percentage of males with smoking than females. With the data shown with this particular style of graph, it helps us see easier and quicker than just with a generic stacked bar graph that the smoking and gender variables are related to each other since the numbers are percentages instead of just counts. So my next graph is a histogram. I thought ejection fraction was my most interesting variable, so I did a histogram to show the distribution of the patient's ejection fraction. To calculate the correct bin size, I took the square root of the number of rows of the data and got 17.29, so there's 17 different bins for this graph. The average ejection fraction is 50 to 75%, so you can tell how the graph, in this graph, the average is definitely below the normal range and skewed towards the left, which means our median will be higher than our mean. It also appears to be a little bimodal with a lot of patients falling the bins about 35% and at 60%. We can't definitely see outliers like on a box plot, but there's definitely a wide range of values. And so these are two side-by-side box plots. The box plot on the left is of ejection fraction by gender. We can see that females had a wide range of values and a higher median. Males had a smaller standard deviation away from the median and several outliers. Overall, this graph is showing females generally had higher ejection fractions compared to men. The graph to the right shows ejection fraction and whether the patient died or not. Patients who lived had higher ejection fractions and had a median about 8% higher than the patients who died. However, of the patients who did die, there were several outliers who had high ejection fractions and still did not live. Looking at these two graphs, I would think that maybe because females had higher ejection fractions on general, that those with higher ejection fractions tend to live and that more females would live compared to males. However, with the stacked bar graph that we saw earlier, there was almost no difference in death by gender, which is really interesting to me and shows that there are a lot of variables at play here. So next I did two scatter plot graphs. The top graph is ejection fraction and age. I expected to see a correlation here and I thought ejection fraction would go down with age, but that's not really the case. There really isn't much correlation or relationship between these variables, and I'll go over correlation between numeric variables later, but there really isn't much correlation between any of my numeric variables. The two variables that had the highest correlation were sodium and serum creatine. As serum creatine increases, the levels of sodium generally decreases. I don't know enough about what's happening with both of these on a molecular level in the body, so I'm not really sure if this is a relationship that happens in real life or if this is just a sample from the data. So this is a facet wrapped bar graph with three variables. I selected the age variable that I had made into a categorical variable with ranges, the gender of the patient, and the death variable of whether a patient died or not. A patient's death is represented by the red color. So the patients died in the higher age ranges for both males and females. The fewest number of patients died in the 40 to 49 age range. The graph shows the higher percentage of patients died if they were older. So if a patient died, it was somewhat correlated to age. In addition, gender does not appear to be much of a factor for if a patient died or not, according to this graph. About the same number of males and females died for each age range. The main exception for death versus age or gender versus age is the 90 plus female category, but there were only 2 females in that category, so it's not a good representation of the data set as a whole. So for my special graph, I decided to do a heat map. The categorical variable of platelet count in ranges is on the x-axis, and the categorical variable of whether the patient died or not is on the y-axis. And the ejection fraction variable is overlaid on the map, so a darker color represents a smaller ejection fraction. The patients that died and had moderately low or normal platelet counts had the lowest average of ejection fraction. Patients who lived and had high platelet counts as the highest average ejection fraction percentages. The graph probably would have been better if I had variables that related more to each other in a meaningful way. Platelet count isn't super important or super interesting, but was the categorical variable with the most categories. There were also only a couple platelets with severely low platelet counts, so a variable with a more equal distribution would have been So for multiple linear regression, I predicted age variable from the other numeric variables. Part of the correlation matrix is the bottom table. And the whole table showed there to not be very strong correlations between the numeric variables. The highest correlation was between sodium and creatine S at negative 0.189, with 0 being no correlation, and perfect overlapping correlation would be -1 or 1. So therefore, none of the numeric variables are very correlated at all. I built the model and found the regression estimates. This is the equation for the line of best fit generated by the model on the left side. The adjusted R-squared value is 0.02135, so the model gives a good prediction, about 2.1% of the time. To tell which variables are important in predicting the age variable, I applied the AIC method. 4 of the variables were removed, so just creatine S remained. Still, it only gives a good prediction 2.2% of the time. To test the model, I used 1.2 for creatine, and the output is the lower numbers on the bottom of the screen. The age was estimated to be between 37.28 years and 83.66 years, so overall, this is not a super good model to estimate age. And so using logistic regression, I created a model to calculate the odds of dying with the other numeric variables. In the generalized linear model, there were 6 variables, and that's shown in the top left table. After applying the STEP AIC method, the platelets variable was removed for a total of 5 variables, which is the upper right table. This gives us the log of the odds of death. So for example, every 1 unit increase in age, the log of the odds increases by 0.053, assuming that the other variables remain constant. So that's a little bit hard to understand. So if we exponentiate the log of the odds, we get more interpretable results. The table for this is in the middle. If all the other variables are held constant, a 1 unit increase in age will increase the odds of dying by 5%, which is calculated by subtracting 1 from the coefficient since the number is above 1. For a coefficient that's under 1, such as ejection fraction at 0.935, the coefficient is subtracted from 1 and represents a decrease in the odds. So for every 1 unit increase in ejection fraction, the odds of death decreases by 6.5% if the other variables are held constant. I then put in some sample values that could be used to predict if the patient would live or not using the model. I used the age of 64, creatine phosphokinase equal to 130, serum creatine equal to 1.3, sodium equal to 130, and ejection fraction of 40%. And I got the output that's at the bottom of negative 0.7264487. And since the negative number, a patient with these values would be predicted to live. So looking at confidence intervals, I didn't have a lot of details about exactly where this data was from, but I'm assuming it would have probably have to be patients who have already been diagnosed with cardiovascular disease, or at the very least at high cardiovascular risk. So that will be our population. For one sample inference, I'm going to estimate the proportion of patients who also have high blood pressure within my particular population. I made a table to see how many patients had high blood pressure and then enter that into a prop.test function. I'm showing the results I got from that function. So from the results that I got, we are 95% confident that the percentage of all patients diagnosed or at risk for cardiovascular disease who also have high blood pressure is between 29.77% and 40.86%. Out of the 100 truly representative samples, we would expect 95 to capture the true parameter of our population. And so for 2 sample inferences, I looked at males and females as my 2 samples to see if females are on average older than men. In general, women live longer than men, but I wanted to see if it holds true to a population that is at cardiovascular risk. So my population 1 is going to be all the females diagnosed or at risk with cardiovascular disease, and the population 2 is going to be all the males diagnosed or at risk for cardiovascular disease. My goal is to estimate the mean sample for the females minus the mean sample for males. I did a t-dot test and my confidence interval was -4.3 and 1.13. And so since the confidence interval goes from a negative number to a positive number, it's possible that the difference between the 2 proportions is actually 0. So we can't conclude that one sample has a higher proportion than the other. Another way of saying that would be we can't say with almost certainty that the average age for males or females is higher than the other outside of our samples in the population itself. And so this is all the information that I have for my presentation. These are just my references that I used for this presentation specifically. So that is all that I have. Thank you so much for a great semester.